So yeah, basically, yeah, like I said, so yeah, the presentation will be about domain adaptation in the era of foundation models. And this is a presentation of my PhD. My supervisors are like Stéphane Lathuilière, my thesis director, working today at INRIA Grenoble, Vicky Calogeton, who's a professor at École Polytechnique, and Slim Essid, who's a senior research scientist at NVIDIA. So let's get started. So, I mean, in computer vision, if we have to take the three most important tasks, or the three most popular tasks, would be image classification, where the objective is to assign, I mean, an image level label to any given image. We have object detection, where the objective is to like create some bounding boxes around objects and also like give them a semantic class. And then we have the task of image segmentation, which is our task of interest today, where the objective is to actually assign a class to every pixel in the image, basically. And when we take the task of semantic segmentation, if we have a high resolution image like this one, to be able to segment it fully, like pixel by pixel, it takes a lot of time. It takes a lot of time because it has around 2 million pixels. As you can see, this is an image taken from the Cityscapes dataset, a really popular dataset in the semantic segmentation community. And yeah, like I said, to be able to collect millions of images like this creates a bottleneck, basically an annotation bottleneck. So being able to collect a lot of data in this task is a little bit more difficult than than image classification, for instance. So something we can say is to do synthetic data training, where the objective is to say, okay, maybe I cannot collect a lot of images from the from real life. It takes a lot of time. What if I use a game engine? So today we have game engines that like can generate a lot of images. As you can see, we can take a game engine of a really good video game that can have really realistic images. We can take, for instance, GTA video games, and then take a lot of generate images. And since the computer generating the images, the computer can also generate the annotations of these images. So we can have a huge amount of synthetic data from just using game engines. And then if we take this labeled synthetic data, and then we train a model on this synthetic data, and then also we do the test on the same synthetic data. I mean, if the training was well done, usually we have high accuracy on synthetic data because the model has been trained and tested on the same kind of data. So everything is good, we're happy. However, if we do test this synthetic trained model on real life data, because that's what we care about, we see that we have low accuracy on real life data. And this is because of what we call domain shift. So the question we're going to try to answer is, what is domain shift, basically? So the domain shift we're going to talk about today will be basically a domain shift in terms of appearance. As you can see on the left, this is synthetic data, synthetic images coming from GTA 5. On the right, we have real life data, as you can see. And basically, this is what we call synthetic to real domain shift. I mean, the classes are the same. We have the same car on the left, and on the right as well. But as we can see, the texture is different. The illumination is different. And this is the kind of domain shift we will try to tackle today. The domain shift that is related with the appearance of images. Same thing goes from real to adverse weather conditions. I mean, on night images, objects are more difficult to recognize than on daylight images, as we can see on the middle. So basically, these are the two main domain shifts that we will try to talk about today. And one of the main settings that the research community developed in order to tackle this domain shift problem is unsupervised domain adaptation, where we assume that during training time, we have access to labeled source domain, but also some unlabeled images from the target domain, because these are the ones that are hard to collect. And then during inference, we need to have a model that can work on what we call here distribution shifted target domain, basically. So we have a kind of difference in distribution between the source and target domain. And that's the objective of unsupervised domain adaptation, which is to train a model using labeled source, labeled data, and unlabeled target domain, which is distribution shifted. And then yet at inference, we want to have a model that can work well on this target domain. So this is unsupervised domain adaptation. And basically the objective, in order to do so, if we take a segmentation model and then we give it synthetic and real life data, if we look at the feature representations of these two domains, Basically, we're gonna see if we project this on a two-dimensional axis using some PCA algorithms, some projection algorithms, we see that those points are very far away from each other, as you can see. And the objective of unsupervised domain adaptation is to take these two distributions and then try to learn what we call domain invariant features by basically learning the features that are invariant from one domain to another, and then have them basically collapse into one area. Like basically, we should not be able to classify between synthetic data and real life data. If we are able to do so, then we achieved what we call adaptation. Then for the model, for the segmentation model, synthetic data and real life data is basically the same. So that's the ultimate goal of unsupervised domain adaptation, which is to learn domain invariant features. And to do so, like we have seen many paradigms in the community. The first one were discrepancy-based methods, where the researchers were trying to create some statistical distances, and then they were trying to minimize that domain training, like maximum mean discrepancy and other metrics like that. We saw also adversarial-based methods, where the objective is to try to train in an adversarial way a discriminator to be able to classify between features coming from source domain and the target domain, and it was trained in an adversarial way. So we had some like gradient reversal in order to train the source extractor and the domain discriminator in an adversarial way. And the last methods that were really popular in the last years are self-training, where the objective is to actually basically train a model on the target data using its own predictions, what we call pseudo-labels. And this is the last family, which is like a family of methods, which is self-training, is what we're going to see today. So another question we can ask is why supervised domain adaptation is important. This is something that is used in many domains. It can be medical images when it comes to, for instance, classifying tumors from one MRI machine to another MRI machine. It can be, for instance, autonomous driving. We may want to train an autonomous vehicle to drive fully autonomously in New York, for instance, and then have this same car work really well in Paris or London or other cities. It can also be satellite images. Areas are different, but we may not be able to train on satellite images coming from the whole world. So basically, we want to maybe train our model to recognize areas on a given region and still have this model work reasonably well on other regions of the world. So unsupervised domain adaptation is used in many areas, and that's why it's really important to work on this setting. And during my PhD, if we look at this, this image, as you can see, since 2012, we have the Alex moment, which created for us deep learning. Deep learning started being really popular, and we saw in 2016 the ResNets appearing, mask RCNN, deep learning architectures that are evolving, and then also deep learning architecture that are really tailored for given tasks like object detection, semantic segmentation, and so on. And since 2021, something happened where we started seeing the appearance of huge models, like CLIP, for instance, a model that is trained on 400 million images. So the size of the datasets got extremely big, but also the size of the models. As we can see in Stable Diffusion, it's trained on 2.8 billion image text pairs, ChatGPT 300 billion tokens, SAM as well, which is trained on more than 100 billion masks. So since 2021, we had this appearance of these really big models trained on huge data. So they are big because they have a lot of parameters, but also they have been trained on a lot of data. And basically, in this 2021, we can try to maybe do a split between two eras. We had the supervised learning era from 2012 up to 2021, but then now we are in what we call the foundation models era, where we have these big models trained on a lot of data. And that's when I started my PhD. I started my PhD in late 2021. So the objective, the question we're gonna try to answer now is actually the following: is how can foundation models, since we are in this foundation models era, how can foundation models advance domain adaptation for the task of semantic segmentation? So this will be the topic of the presentation. And in order to answer this question, we're going to try to tackle some settings and then see how can foundation models help us advance that. The first one is going to be one-shot domain adaptation that we will see later, but the objective here, we assume that we are in a resource constrained scenario where we only have one image from the target domain. We're going to see domain generalization, where we don't assume having absolutely no knowledge about the target domain during training, and we only have access to here to the label source domain, and still we want to generalize to completely unseen domains. We're gonna also, like, for the sake of time, but we also tackled during my PhD that black box domain adaptation, where we assume not having access to the source data, but to an API model that can give us some predictions that are completely like one-hot predictions. So we don't have any knowledge about neither the weights of the API model or the logic associated to its predictions. And still we need to use this model to train a local model using some unlabeled data from the target domain. And the last setting is a setting where we tackle open vocabulary semantic segmentation, which is a setting that uses a foundation model. In this case, it will be CLIP. And yeah, basically, the three works we're going to present are these three: one-shot domain adaptation, domain generalization, and open vocabulary semantic segmentation. So for the sake of time, I will skip a black box domain adaptation. So the first one was a CVPR workshop, 2023. I'll present then after that domain generalization, which was accepted at CVPR 2024, and the last one, which was accepted last year at ICCV 2025. So the first one is DATUM, the name of the method, and the question we're going to ask is how can we, we're going to try to answer basically is how can we overcome a data scarcity in the target domain during the training phase. So basically, like I said, one-shot domain adaptation is slightly different than unsupervised domain adaptation because we only have access to only one image from the target domain. So we have the labeled source domain, one image from the target, and still we need to build a model that is that can have a good performance on the target domain during inference. So at the time when we started working on this problem in 2022, state-of-the-art UDA methods were really good, really popular. Like the classical UDA methods, like DA former and HRDA. These are two existing methods that are really good when it comes to unsupervised domain adaptation for the task of semantic segmentation. But when we take these methods and apply them to unsupervised domain adaptation, when we put them in this resource constraint scenario, we see that their performance drops heavily. Like we take DA former, it drops by 20% on MIOU, and same thing for HRDA. So basically, MIOU is the metric we use for semantic segmentation. Basically, given an input image, we have prediction map and ground truth map, and then we compute the area of overlap divided by the area of union. So if we have the same, if the prediction map is exactly the same as the ground truth, we'd have an IOU of 100%. So yeah, state-of-the-art UDA methods, they struggle in unsupervised, in one-shot domain adaptation. And the previous works that we're doing, that were trying to solve the one-shot domain adaptation setting, were basically using style transfer. It was popular at the time, style transfer. So they were taking source images, they were taking the single target image, and they were pasting basically the statistics of the target image onto these stylized images in order to create a new stylized dataset by keeping the same annotation. As you can see, the annotation didn't change before and after style transfer, but the input image now has some statistics coming from the target image. It was done like using some instance normalization techniques. Basically, the question we ask is, like, here we are doing only style transfer, but can we enable both content and style diversity? Because that's the ultimate goal. Here the object didn't change in terms of shape. As you can see, the track on the right is the same as the track on the left. But in this foundation models era, can we enable both content and style diversity? This is the question we're going to ask. We're going to try to answer basically. So in 2022, we had the emergence of what we call text-to-image diffusion models. So basically, these are models that are trained on a lot of images, like we saw earlier, like billions of images, and basically they are trained in using a reconstruction loss in order to basically create new images. So diffusion models at inference time, they can generate for us photorealistic images, and still they give us like the ability to control the content and the style. And this is what we're going to use in our setting of one-shot domain adaptation. So basically, the pipeline is simple. We're going to take a text-to-image diffusion model. We're going to give it some text conditioning, as you can see, a photo of a car, a photo of a bus, photo of a motorcycle, etc. And then we're going to generate some images, right? So here we do this. We can generate some images. And then we're going to take these images and then plug them into this existing UDA methods that we saw earlier. So like we said earlier, UDA methods struggle in one-shot domain adaptation, but because they have been built by taking into account that they're going to have access to a lot of images from the target domain. And since in one-shot UDA we don't have a lot of images, let's try to generate synthetic data and then plug this data into existing UDA methods. And now we have what we call a pseudo-target domain, which is actually a synthetic domain generated using a diffusion model. So here UDA methods, they're gonna kept. We are not gonna make any change into these existing UDA methods. We are going to just generate synthetic data, basically, as you can see. So now that we use these UDA methods, as we can see, the performance improves. Like a DA former plus a diffusion model now, like data coming from a diffusion model, the performance improves by 4% on MIOU. Same thing for HRDA. When we plug this synthetic data into existing UDA methods, they improve. And this is the results we got by going from GTA, which is a synthetic domain, to cityscapes. So generating synthetic data using a diffusion model and then giving it to existing unsupervised domain adaptation methods help us to have good performance on cityscapes dataset, which is a real-life dataset. Basically, it's a dataset composed of images from German cities, basically. So we are happy, we have an improvement. So synthetic data helps us to do domain adaptation. But if we look at the generated data, we have a photo of a car that looks like this. We have a photo of a traffic sign that looks like this. Same thing for the bus. Same thing, here's the motorcycle image. Basically, these images are very different than the target domain we want to mimic. Basically, this is what we care about. The target domain, these are images from cityscapes. This is how German cities looks like. And the diffusion model, which at the time we use stable diffusion cannot generate images that looks like German cities. So we still have a discrepancy between the generated data and the target domain that we care about. So the technique we're going to try to do now is how can we generate data that is aligned with the target domain. So the technique we're going to use is DreamBoot. So DreamBoot is a technique that helps you to personalize a diffusion model to generate the new content, basically. Like let's say we have an image of a dog that the stable diffusion has never saw before, but DreamBoot helps you actually take a diffusion model and then inject this new knowledge of this new dog into its pre-trained knowledge. And basically, you can generate new images of this same dog in new environments. And this knowledge of this environment comes from the pre-trained knowledge of the diffusion model. And this is what we will do. Basically, if we look a little bit more into details of DreamBoot technique, it's a fine-tuning technique that takes images of the dog and takes a pre-trained diffusion model. And then what it does is that it associates a unique identifier in the text prompts, because it's a text-conditioned stable diffusion model. So it takes a new token, a really rare token that will be associated to these new images, to this new concept, basically. And then by doing fine-tuning, like by training the model to regenerate these images of the dog, and still, again, like I said, associating this rare token to these new images, we're going to have a personalized text-to-diffusion model, a fine-tuned model, basically. And this fine-tuned model, when it is prompted with this rave token that we see here, like this and then we put the rave token dog in the beach, we see that we have this same dog that we had here in the beginning generated in the beach. So the model can still recover the dog, but still can also recover the environments around the dog. So here the beach, and here also the colorful carpet. And that's what we will do in our case. We will personalize the text to diffusion, personalize the diffusion model to generate data that looks like the target domain. So the target domain will be the concept that will be injected. Basically, it looks like this. So we will fine-tune our diffusion model with the single target image using DreamBoot. So we take our target image, the only one we have access to. We're going to do some multi-cropping strategy. And then we get a few samples from the single image we have. And then we're going to associate, like as we can see here, this rare token to these images. Then we're going to fine-tune our diffusion model. And by doing that, now we can generate, as you can see on the right, which is exactly like this same step. We're going to put a photo of a V-Star car. And this V-Star now, by generating new images, we're going to get cars that looks like, which is more realistic, basically. That looks like the target domain that we wanted to mimic. So basically, that's what we'll do. But what we will do, basically, we use class-specific prompts, like I said, plus this unique identifier that we use during training to increase the image diversity, but also the alignment with the target domain. And now we move from this to this, basically. Here, as you can see, a photo of a traffic sign. When we give it to a text-to-image diffusion model, it gives an image that looks like this. Whereas now, if we use this neural token that we injected with the personalized text-to-image diffusion model, we can generate images that are more aligned with the target domain. Same thing. So basically, we go from images that looks like this to images that looks like this. And the images here in the middle are more closer to the target domain than the initial images, right? And that's what we wanted, actually, basically, at the end of the day. We wanted to generate images that are closer to the target domain. So basically, now, if we plug this new data into the existing new DA methods, we see that we improve. We keep improving. So our data, our new data that we generated using our personalized diffusion model is helping us to actually segment really well the cityscapes dataset. And the improvement, we have an improvement of 4.2, 4.7 on two different methods, DA former and HRDA. So this is something that we definitely want. And one question we can ask is, how long should we fine-tune the text-to-image diffusion model? Because like we said, Greenboot involves fine-tuning of a diffusion model. So if we look at the training steps, basically, of the fine-tuning, the 0 step basically means that the model hasn't been fine-tuned. It means that we are using the stable diffusion as it is. As we can see, the images are really, like, definitely not realistic and do not look like the target domain that we want to mimic. After 200 steps, this is the images that we used also in our final paper. But if we kept the training going, if we kept training at 800 steps, we see that the images are even more closer to the target domain. So here, these images are even better for adaptation, right? This at 800 steps, we have images that are really close to the target domain. But when we look at the results at 800 steps, if you use the generated data after 800 steps of fine-tuning, you get a decrease in performance on both methods. Why? Because actually, we lose diversity. That's the problem. If we go back to this slide, you see the images are nearly the same. And what we want in order to do adaptation, you still want to have like diversity. You still want to preserve diversity and still have a certain degree of alignment. So there is a sweet spot that we need to find between fine-tuning diffusion model, but still keeping its initial diversity. So that's why we did some ablation studies in the paper, and then we saw that at 200 steps, this is the best thing to do, because it's the sweet spot between having diverse images, but still aligned images with the target domain. So when we do synthetic data generation, you want to also make sure that you don't lose diversity. Diversity is extremely important when it comes to like having deep learning models that can generalize. And yeah, as takeaways of our method basically is that the first thing to do that we believe is important is personalizing text-to-image diffusion model is really important, especially if you have a target domain and like you don't have many images of the target domain. I believe that personalizing the diffusion model on these few images coming from the target domain is extremely important, and it can generate a lot of data, but it requires like careful fine-tuning. And as we can see here, we generated synthetic data, and then we used like self-training, because HRDA and DA former are self-training based methods. So that's what we did. But again, we didn't have any filtering on the generated data. As you can see, we generated data as they are, and then we trained our unsupervised domain adaptation methods on this unfiltered synthetic data. And I'm going to come back to this filtering at the end of the presentation. But here in our method, we didn't do any filtering on the synthetic data. Now, a second question we can ask is, what if we don't have access to the target domain? Basically, it's the following. We don't have access to the target domain, meaning we only have access to the source domain. But during inference, the target domain can be anything. It can be images coming from different regions of the world, from different weather conditions, and we don't know what we're going to expect at inference time. In this case, we are in a domain generalization setting. So it's a slightly harder setting than one-shot domain adaptation. And this is the second work that we will present. So the question here is, how can we train a model on a source domain only and still generalize during inference to unseen domains? So basically, this is called domain generalized semantic segmentation. And as we can see, it only uses labeled source data only, and still we need to test on unseen domains. So again, at the time in 2022, 2023, stylization was like really popular, and many methods were doing what we call domain randomization by actually doing some kind of fancy stylization on the initial source images in order to create many copies of that same image and training on all these copies. So this is a kind of style diversification, but they were again only focusing on style diversification only. Content was not like taken into account. As you can see, it's the same image. The car is in the same place. We don't have new objects in the image. We don't have new composition of the image. Like it still remains the same. So this was the first family of methods that were trying to do domain generalization. They were trying to do it through style diversification. The second family of method actually was doing something slightly different. But actually, it was at the time, it was like CNN-based methods. They were, as you can see here, this is VGG, or even CNNs. They were doing it on CNNs as well. But the idea was to take many images from the source domain and then actually erasing domain-specific features from these images and enforcing the model to learn what we call domain invariant features. Again, it's the same problem. So we try to learn domain invariant features by eliminating domain-specific features by having some instance normalization methods that were doing some renormalization tricks. So this is the second family of methods that were like designing some tailor-made modules. But as you can see on the left, this is the domain randomization techniques, the tailor-made modules. But both of these methods, actually, this family of methods, they were using ImageNet pre-training. And they were also using some CNN architectures. And we were, at the time, we were in 2023, 2024, and we already have like different new models that are first transformer-based, that have large pre-training, as you can see, and they also have a lot of generative power when it comes to diffusion models. So the question we're going to ask is, how can we use now foundation models? So basically, we felt that domain generalization was the setting of domain generalization was a little bit lagging behind the latest advancements in deep learning. And we're going to use the new models to basically provide a new starting point for this setting. So the first question we want to try to answer to when it comes to domain generalization, the first one is feature representation. You want to have good feature representations. Like I said, I need robust feature representations to generalize to any domain during inference. One thing I have is the Clip Vision encoder. Clip was released in 2021, and we saw that it has like robust feature representations because of its contrastive learning. It has been trained using a contrastive learning fashion on 400 million text image dataset crawled from internet. So basically what we will do is that we're going to take a clip image encoder. As you can see, we have a decoder. In our case, it will be a mask-to-former decoder. And then we're going to do the training, supervised training, classic supervised training on the source domain that we have, which is actually basically the only thing we have access to. So we're going to do supervised training. But we're going to keep the clip encoder frozen in order to not have catastrophic forgetting and to keep its initial feature representations. So the only thing that will be trained here will be the decoder. When we do this, we see that we improve. We improve the results by training on the source domain only, and then we even outperform all the methods. As you can see from the left, IBN, ISW, Shade, TLDR, Modify, and HRDA are existing methods that were doing domain generalization. Every method has its own technique. Some papers, some works were doing like texture randomization, style diversification, like I said, tailor. They were injecting some modules in the architecture, but as you can see, just using a frozen clip and the mask-to-former model, which is a really recent decoder, we are outperforming the existing methods on 3 different datasets. So these datasets have not been seen during training. They are target domains that have been provided to the model during inference, and we see that we improve over all the existing methods. But I mean, it's not comparable because here we are using clip, which is a stronger vision encoder, a stronger decoder. But rather than being comparable, what we want to do here is to provide a new initial point, a new initial starting point, so that upcoming works will built on top of this new foundation model. And this is what happened actually in the next few years, like in 2024, 2025. Many methods are now, all the methods that are doing domain generalization for the task of semantic segmentation, they are using like either clip models, dino models, but basically, yeah, foundation models. So this was the initial, the purpose of this work, is to provide a new starting point for domain generalization. But we are not going to stop here. So here we have a clip model that is already better than all the existing state-of-the-art works. But we're going to keep doing something more. Another question we ask is, how can I simulate plausible target domains? I don't know the target domains that I will have during inference, but can I simulate them already during training? So basically, again, we're going to do synthetic data generation. So I need to generate sufficiently diverse synthetic data. We saw earlier that having diverse synthetic data is really important. That's what we'll do here. And it's even more important here as we don't know the target domain that we will have. So we're going to use, again, text-to-image diffusion model to generate photorealistic data using text conditioning. And something that we will do is that we're going to try to increase diversity already from the text conditioning by using a large language model. At the time, Llama was really popular, so we're going to use Llama by actually asking it to give us a lot of prompts, a lot of text prompts, as you can see here, a photo of a busy road in daylight, etc., a snapshot of a man crossing the road, by actually asking the model to give us some prompts that depict urban scenes, because the only thing we assume is going to be the same going from the training to the inference is that we're going to have urban scene. So this is the only metadata that we know. And basically, by giving this text prompts to a text-to-image diffusion model, it will generate for us a lot of images, really diverse images. And we're going to, since we have this generated data, we're going to do self-training. So this is the first time that self-training is done in domain generalization. So we're going to self-train mask transformer on the generated data using pseudo-labels. Basically, it looks like this. So we have our source training that we saw earlier. We have our generated data that has been generated using a text-to-image diffusion model. And then here we're going to do it in a student-teacher fashion. This is one of the classical ways of doing self-training. So the decoder, we're going to have an exponentially moving average of the decoder, which will be our teacher. Basically, I said that the clip encoder is frozen, so we don't have a teacher for the encoder. The encoder is kept the same. It's completely untouched to basically avoid any catastrophic forgetting. And yeah, basically we have one stream which is completely which is heavily augmented, that is going through the student branch. So the decoder is giving us a prediction on these images, but then this same image is given to the EMA, to the teacher, that is giving us a pseudo-label, basically. So by doing this is called self-training, meaning the student is trained using predictions coming from the teacher. But the teacher is basically an exponentially moving average. It's a smoothened version of the decoder. And basically, we hope that the model is going to keep improving along iterations. This is the assumption that we have. So if we do this, the performance we have before and after doing self-training on different backbones, like if we take like clip, which has a ResNet 50 backbone, ResNet 101, CovNet large. If we do self-training, when we plug self-training, as you can see, this is the MIOU, the average MIU computed on 3 different datasets, cityscapes, BDD, and mapillary. We see that the improve is really marginal. As you can see, we marginally improve over the backbones, different backbones, but still the results is not really satisfying. So self-training doesn't really work if you do it this way. Why? Because the images that we have here have never been seen by the model. So it's really hard to have reliable pseudo-labels, because this self-training technique is definitely tied to actually having really good pseudo-labels. If you don't have good pseudo-labels, self-training would not work. So as you can see, this is something we see here. We marginally improve. So self-training until now doesn't work. And actually, it's normal. As you can see, when we look at the data, this is the image. This is an input image that we have. When we give it to the teacher, this is the prediction it gives. For instance, this carpet is segmented as a sidewalk, even though we know that it's not a sidewalk. This is not this carpet should not be segmented as a sidewalk. Same thing for here. Here we have sidewalks in the middle of a garden, for instance. We have here also this umbrella that is segmented as a building, even though it's not a building. Also here, as you can see, the pseudo label is really noisy. We don't have a really good segmentation of this traffic light. Basically, you can call it a traffic light, and that's the reason why self-training didn't work. As you can see here, this is the highlighted regions that I showed you. So yeah, we don't have a good segmentation of images, of these synthetic images. So yeah, like I said, we have noisy pseudo-labels. As you can see here, we have noisy pseudo-labels, so we can self-training doesn't work. But something we can do is the following. How can we improve the quality of pseudo-labels? We have segment anything that was released. It was released like 4 months ago. 4 months, I mean, at the time, it was 4 months ago. It was really good at segmenting images, but it was giving mask predictions, meaning it didn't give us like it didn't give us the semantic classes associated to the mask. It was only able to give us like really sharp, good mask predictions. And basically, SAM is a model that is, again, trained in a recursive way, as you can see here, from the model to the data, but the data is really huge. We have 11 million images, more than 100 billion, more than 1 billion, sorry, more than 1 billion masks. And yeah, it's a transform-based method, as you can see. And yeah, it can basically do what we call here, it's a promptable segmentation model. Basically, you can give it a segmentation prompt. It can be like some dots in the image, some bounding boxes, some coarse masks, and it can give you the mask associated to these geometric prompts, basically. And this is the quality of data, that SAM has been trained on. As you can see, like really sharp images. So like the key thing is about the data. It's all about the data. So like for the SAM model, really the annotation is extremely nice, extremely sharp. So that's why the model is able to give us really nice mask predictions. And that we will use this power to our advantage here. Basically, we will use it to improve our pseudo-labels. As we can see here, we have our noisy pseudo-label, and we're going to try to improve it to get this. How do we do that? We have what we call here a prompt extraction module. So here, this is a semantic segmentation map, which is basically a class level mask. Like this segmentation map can be split into different into binary masks, and each binary mask is going to be associated to a class, basically. So here, as you can see, we have C. C here is the number of classes, and then, for instance, for this person, we can have a binary mask that corresponds to only this person, and also the very distant persons here that are red here. But they will be filtered using some filtering mechanism that we have implemented, a filtering algorithm that takes out these noisy masks. So only the person remains. This is the only like a connected component that remains. And then we're going to extract from it some points, some dots. And since we know that, again, like I said, we know the class of these points, we know that they belong to the class person, we're going to give them to the segment anything model. Segment anything model will give us the nice mask corresponding to these prompts, to these 4 dots, and then we're gonna do this for all the classes. And then we're gonna merge all the binary masks, all the masks that are given by segment anything model. So it's a way to reconstruct the segmentation map, starting from the noisy segmentation map that the teacher gave us. So basically, SAM is going to be used to actually refine the segmentation map that we have using this prompt extraction module. And then when we have like some, for these black pixels, this is a case where we actually have two masks that are overlapping. When we have 2 masks belonging to 2 different classes that are overlapping, we're going to try to play it in a really secure way. So we're going to discard all the intersection pixels, and then assign to them a black pixel, which means that they are completely undefined, which means also that we are not going to supervise our model on this region. All the black pixels will be discarded. And if we do the same technique for all these images, as you can see, we have many black pixels that start to appear. The umbrella got completely discarded because it's an overlap. It's an object that is completely unwanted, and it may also be an intersection of different masks. So this is something that we completely discarded. Same thing for here. As you can see, the mask got even nicer, and so on. So this is a technique that is going to be used. Like we're going to use them to refine the segmentation maps, the noisy segmentation maps, and then we're gonna also discard the ones that are intersected between different masks. So we don't want to have noisy pseudo-labels. The most important thing in self-training is that you don't want to train your model on some noisy labels. Now, when we plug our, as you can see here, we have the noisy pseudo-labels, we extract prompts from it, and we give them to segment anything model. So segment analytic model takes as an input the input image, as you can see here, goes to here. And then we have the geometric prompts, which are basically just dots. And then we get back the refined pseudo-labels. And then we're going to use these refined pseudo-labels to actually supervise our student model, which is basically the decoder. When we do this, the performance increases. As you can see, again, evaluation on different backbones, ResNet 50, ResNet 101, complex large, the performance improves. And this is the name of our method, final method, which is clouds. As you can see, the performance improves consistently across different architectures. Another question we're going to try to answer here is how much synthetic data we need. Because as you can see here, we have synthetic data, but we can generate as many as we want. Like we can generate 1,000, 100 million, 1 billion images. But what we saw is that after 5,000 images, our model started plateauing in terms of performance. So this is the performance of our final model. And this is here, as you can see, a bar plot of the number of images that we generate. Of course, going from 100 to 500 is good because you get more images, more diversity, more knowledge, and the model keeps improving. But after 5,000 images, the model started plateauing. And this is because of many reasons. One reason is that actually the fact that we froze our clip encoder, it also restricts us. So the only parameters that we can have, that we can basically update is the decoder parameters. So this is one problem that we have. So basically we didn't want to, like at the time, we didn't want to make it complicated by putting some adapters inside the clip encoder or stuff like that, but we just kept it frozen. And also this also it makes adaptation a little bit harder when you freeze completely the encoder. And we know that the feature representations are in the encoder, not in the decoder. This is what is important when it comes to feature representations. So the fact that we froze our encoder is something that also made this plateau happening, the plateau that you see here after 5,000, but also the diversity of the images. After generating a certain amount of images, we started seeing that like diversity was a problem. So we started seeing like the same images getting back again and again. Also our pseudo-label refinement module was not completely perfect. Sometimes we also had some noisy pseudo-labels. So for all these reasons, I think that's why we started reaching a plateau very early. This is because of these three reasons. Like the first one, freezing the encoder also like makes the adaptation harder. The diversity, the lack of diversity that we had after generating like images using diffusion model, at some point we started having the same image getting generated again and again. And also the fact that we have also like the pseudo-label refinement module was also like lacking some, was also like not perfect. And if you go to in the paper, you will see that we have shown some failure cases of our pseudo-label refinement module in the, I think it's in the appendix of our work. And yeah, as takeaways, basically, I believe that using an LLM to increase text diversity, basically this, like we did, is something important. Retaining the pre-trained knowledge of clip also is important, but again, like I said, it also like harm us when it comes to adaptation. So maybe today using adapters inside the clip encoder or like only training the last layers of the clip can be interesting, at least better than freezing completely the encoder, and then using SAM to improve the self-training pipeline. So again, here, as you can see, we use different foundation models to advance the domain generalization, the domain generalization setting. Again, here we don't have we have no filtering on the generated data, as you can see. And something that is important is that for this self-training loop to work really well, we should have good initial pseudo-labels. So if you don't have good initial pseudo-labels, we cannot extract reliable geometric prompts from it. And if we can't extract geometric prompts from it, it's nearly impossible to recover and to improve the initial pseudo-label. So yeah, to have this module work really well, like going from the teacher to segment analytic model back and forth, we should have like good initial pseudo-labels. And the last work we're going to talk about is going to be about open vocabulary semantic segmentation. So we're going to try to see a little bit how foundation models are directly used for the task of semantic segmentation. So basically, in open vocabulary semantic segmentation, as you can see on the image, we do not assume, because something we did here in the first work and the second one, we assume that we are in a closed set setting, meaning that the model is can only segment a fixed set of classes. Like if it's cityscapes, it's only 19 classes. If it's I don't know, ADE, it's ADE dataset is only 150, and so on. But in open vocabulary, we assume that we want to segment any class. And basically, in order to do that, we should use clip, because clip has a text encoder, so you can prompt it with any class you want. So this is what we call open vocabulary semantic segmentation. So basically, these are two works that exist in the literature: clip denoiser, SFP. Clip denoiser was presented in ECCV 2024, SFP in ICCV 2025. So these are what we call training-free open vocabulary semantic segmentation models. Basically, they are models that can, again, segment any class given any image, basically. So as you can see here, they have like they mainly focused on the improving the visual features of clip. So like I said, open vocabulary needs the clip vision encoder and the clip text encoder. And most of, as you can see, these are the main figures taken from these two papers. As you can see, most of the figure is about the vision encoder. When it comes to clip denoiser, this whole green area is about how to improve the vision features of clip in order to achieve a better open vocabulary semantic segmentation while staying training-free. Same thing for here. This whole region is about improving the text, the image representations. But the text prompt is something that has been a little bit used as it is, as in its default way. As you can see, these are the prompts that are given, the classes that we want to segment. They are given to the text encoder, and we compute a cosine similarity between the patch features or the image representations and the text representations. Same thing for here as well. We compute cosine similarity to obtain the segmentation maps. And basically, that's how it works. Like when it comes to the text representation, all the existing methods were using what we call the ImageNet templates. This is the classical way of doing classification using clip. Basically, you have your class, you put them into what we call the ImageNet templates. These ImageNet templates actually have been prompt engineered in the original clip paper in order to improve zero-shot image classification on ImageNet. That's why we call them the ImageNet template. We have 80 of them. And then we put this class on all these templates one by one, as you can see, a photo of a road, a picture of a road, a cartoon of a road, and so on. And we do this 80 times. And then we give them to the text encoder. We obtain text representations of these 80 templates, and then we average them. So here we do the average of all the text representations of all these templates, where the name road is plugged into all these templates, and then we obtain a good representation of the task road. And then we do this for all the classes. Basically, if you say, okay, I want to segment these 4 classes, my objective is given any image, I want to find these 4 classes into every image I'm given, you do this for all the classes. This will give you robust text representations for all these classes, one by one, right? So this is how it works. And this is how all open vocabulary methods were working, to do segmentation. Basically, they were using these ImageNet templates that were, again, like I said, engineered for image classification. They were used for semantic segmentation. And we know it's not exactly the same thing. Semantic segmentation is a slightly different problem. And we will see why. So here, like I said, this is how it works. You have images, you have text representations, you obtain your robust text features, right? And then you compute cosine similarity between every patch and all the text representation, and you assign to it the closest one. This is how you do segmentation using clip models. And this is how open vocabulary basically works. So the question we ask is, what if I use only one template? So instead of having 80 templates here, what if I use only one? Like, for instance, I'm going to say, okay, I'm going to use only a photo of A. I'm going to use only a photo of A. So here I don't have the average anymore. I have only a text representation of a photo of a road. For this, it's a photo of a person, a photo of a car, and so on. And then I compute my cosine similarity the same way it's done in all the existing open vocabulary methods, and then I get my segmentation maps. And then what if I do it again using a picture of A? Now I do the same thing, I obtain segmentation maps. And again, I do this 80 times. If I do this 80 times because I have 80 templates, now I have basically 80 different models, because each template changes the text features. And when you change the text features, you also change the segmentation maps. So I do this for all the templates. If I do that, what I see is the following. Now I want to look at the performance of these 80 models. I want to look at the performance of these 80 models, and then here I compute a scatter plot, basically, where on the x-axis I have all the classes that I wanted to segment, and here I have the performance of these 80 models. Basically, what I see is that for each class, some templates perform better than the average classifier. Basically, like this template, for instance, is maybe template number 55, and it corresponds to a blurry photo of something. And then you put this in this something, you put the semantic class. Putting up a blurry photo of a sky and then giving it to all the classes gives you a performance that is like plus 20% with respect to this black line, as you can see, black horizontal line here. It gives you a plus 20%. So using some templates alone performs better than the average classifier. And this is a phenomenon that we see for each class. So for each class, we have some templates that when used alone are better than using all the 80 templates at the same time. So this was something that we were not expecting, basically. We're not expecting to have a big gap. Maybe because when we use the average because we want to have a good performance on average. But here, when we look at class-specific performance, we see that for each class, we have one template that performs way better than the average classifier. And this is a curious observation, and we're going to start asking some questions based on this observation. So that's the first thing. So the first question we ask is, how can we identify the class experts without labels? Because as we can see here, we are able to know these templates because we have computed the IOU, right? So we had access to labels, we computed the performance of all the 80 models, and then we saw that template 55, for instance, is the best one for the class Sky. It performs plus 20% on IOU when it comes to the class Sky, because we had access to labels. But if I don't have labels, can I identify these class experts? So class experts, again, is all the templates that perform better than the average classifier. So how can I do that? How can I identify them without having access to labels? The only thing I have is to use entropy. Entropy, for instance, is one thing I can do. It's an unsupervised metric. I can compute it by just having access to the predictions given by each template. And then I know that when the entropy is really low, it means that the confidence is high, and vice versa. When the entropy is high, the confidence is probably low, and probably means if the model is well calibrated or sufficiently calibrated, it means that the model is making bad predictions. So we're gonna use entropy as a proxy metric for accuracy. And we're gonna do it this way. We're gonna take one template, give it all the classes, as we can see, compute the segmentation maps, and then compute what we call here a class-specific, a class-wise entropy. Basically, to have an entropy value for the class road, I'm gonna take all the pixels that are predicted as class road. I'm gonna compute entropy using this formula, classical formula, minus P log P, and then average over all the pixels. And then do this for all the classes. If I do this for all the templates, one by one, I move to template number 2 with a picture of A, and then I compute a class-wise entropy. Basically, I do this 80 times. Like I said here, we repeat the process for each single template. We end up having a grid. Basically, here, as you can see, it's a matrix where the columns are the templates, and on the lines I have each row corresponds to a class. And basically, I'm going to select top K or top N templates for each class. Basically, top N templates means the templates with the lowest entropy, because that's what I'm looking for. I'm looking for the templates that gave me the lowest entropy, which probably means that the model was correctly predicting these classes. Because if I want to find the class experts, I want to find the ones that predict well. And since I don't have, again, like I said, I don't have accuracy, I don't have labels to compute the accuracy, I'm going to use entropy as a proxy metric. And I will do this for all the classes. For the class road, T1, T3, T4 are the templates that have the lowest entropy, and so on. I do this for the person, I do this for the car, I do this for the pole class. So basically, I have as many experts as classes. And now, in order to obtain the basically what we call the class experts predictions for the class road, in order to construct S1, which is basically our experts on the class road, in order to have like good predictions on the class road, we're going to use T1, T3, T4, and we're going to do the average of the text features using only 3 templates, the ones that were identified using entropy. Instead of averaging over the 80 templates, which is what everyone does, we're going to only average over the 3 templates that we found. And then compute the cosine similarity. And then here we obtain segmentation maps where the class road is well predicted. So I have good predictions on the class road. I assume having good predictions on the class road using these 3 templates, and then averaging them at the text feature level, at the embedding level, basically. and then repeat the process for the class 2. For the class 2, it was 19, 5, and 45. And then we're going to again average here and then obtain good predictions where the person is well segmented. And do the same for all the classes. Here, I did only 4 because I assume having access to only 4 classes. So now that I have, actually, I have as many predictions as experts, basically, for each pixel, I have, each expert is giving me a prediction on its on these pixels. And basically, I want to have one map. I don't want to have as many maps as experts. At the end of the day, I am doing open vocabulary segmentation. So given one input image, I am supposed to deliver one segmentation map, right? So in order to have one segmentation map, now I have many segmentation maps, as many maps as experts. So how can we merge them? Someone can say, okay, we can do the average, for instance, we can do a majority voting. But what we will do is that we're going to try to follow actually the initial message of our method, which is that we have experts, and each expert is good on a given class. If we do the average, we lose this message. So basically, if we take the final map, we take one pixel, for instance, an empty pixel. For now, we don't have a class for this pixel, and we want to give it a class. We're going to look at the predictions of this for experts. First thing we'll do, we will only consider the experts which make a prediction on their class of expertise. Basically, expert number 3 made a prediction, said that this pixel x1 is class 4. Expert number 4, the expert on class number 4, said, oh, this pixel x1 is actually it's a person. So I discard S3 and S4 because they made a prediction, they said they made a prediction on a class that is not their class of expertise. S3 can only, I know that S3 is good when it comes to cars, and S4 is good when it comes to boats. So they didn't make a class, they didn't make a prediction on their class of expertise, so they will be discarded, basically. I will only look at the expert that made a prediction on their own respective class of expertise. So S1, which is an expert on class road, said, okay, this is a road. The expert on class person said, oh, this is a person. So now I have a conflict, basically. I have a conflict between two experts. Each expert is predicting its own class of expertise. So which one do I choose? I take the expert number 2. Why? Because it has the highest probability, softmax probability. So I will, when I have conflicts between experts, I select the one with the highest softmax probability, because this one is probably more confident than this one. So expert number 2 has probably a, I don't know, a softmax probability of 0.8, whereas S1 has only a softmax probability of 0.6. So I'm gonna take expert number 2. In other cases, no. We do have it actually in some cases. No expert makes a prediction on their class of expertise. In this case, we use the CLIP model, which is the average model. So since I cannot trust any experts, I'm going to use the classical model, which uses the 80 templates at the same time. So we have a fallback strategy where we use a default classifier. As we say here, we fall back to the average classifier. And here, when we look at the results, when we plug our method to existing open vocabulary methods, massclip, naclip, and clip denoiser, which are like really recent methods, we see that we improve over different classes, different datasets, sorry, whether it's cityscapes with 19 classes to Coco stuff with 170, we can improve over different datasets. So here, this is Pascal VOC, Pascal 59, and here ADE with 150 classes. So we improve using different methods over different classes. And yeah, another question we ask is how many images we need to compute entropy, because we have access to the training data. And the question we ask is how many images we need to compute entropy to identify the experts. On Pascal VOC, we improve starting from 25 images. So given 25 unlabeled images from Pascal VOC dataset, I can compute a reliable class-wise entropy on all the templates to select the good templates and then improve the method. And yeah, we see that we only improve starting from 25 images. When it comes to this, when it comes to cityscapes, for instance, only one image is sufficient, because actually the cityscapes is really a highly dense dataset. It's a dataset that contains many classes. Like here we see that it has like more than 12 or 13 classes in one image. It's high resolution, so I have a lot of pixels. So I can compute a reliable entropy on many classes. So one image is already sufficient to have a reliable entropy computation. So a reliable class expert identification that is going to lead me to a reliable results, because I have good predictions. Whereas Pascal VOC, as we can see in one image, we can only have 1 or 2 classes. So that's why we needed 25 unlabeled images to start improving. So our method also can work with few images. And yeah, as takeaways of our method, the first thing I would like to point to is that Clip is really sensitive to text templates. The way we construct text templates is extremely important, and few images are enough to detect the class experts in our case. And yeah, basically, something to keep in mind is that inference grows with the number of classes, because like we said, we construct 1 expert per class, and 1 expert is giving us a prediction on the whole map. So basically, we have as many experts as predictions. So in terms of inference, when you have a lot of classes, the inference time starts to grow as well. And yeah, this is one of the downsides of our method. If you are in a setting where like inference time is really important, probably our method is not the best thing to use. But if we are in a really critical research setting where we want to have the most accurate prediction, and we are like fine with like waiting and then to have a good prediction, probably using our method is something that can be interesting, where we use actually this sensitivity to text prompts to our advantage, basically. And yeah, so for future works, I would like to talk about some stuff. Like as we can see here in DATUM and clouds, the first 2 methods that I presented, we didn't have any filtering on the generated data. And we know that the quality of synthetic data is extremely important. And it's even more important today, as we know that, for instance, when it comes to LLMs, they have already been trained on the whole internet, and now synthetic data is something that is used to improve models. So the quality of data matters. And in our case, we didn't do that. Like we wanted to keep it simple. We didn't make any filtering on synthetic data, and yet, I mean, it's already worked. But something we can think about is, for instance, basically. We have something that looks like this. We have a conditioning, we have a generative model that generates synthetic data, and this synthetic data is given to the task model. But basically having filters before and after generation can be something important. But by putting some filtering already on the conditioning, and also after generating images. So this is by putting some, I don't know, some rule-based methods, some human filters, like before and after generation. This is something that can be done in order to improve basically the synthetic data generation. But something that can be even more interesting is having, for instance, a vision language model, a really big model that can handle the filtering for us, because we can put as many rules as we want. We may not cover all the cases, but if we put, for instance, a vision language model that can, for instance, take text as conditioning, look at the generated images, and then see if whether it is good or not for training, and then after that give back the image to the generative model to make some editing, for instance, or maybe change the text conditions. Like we can even like give a sentence to the VLM that can look at the sentence, and maybe it can find some unwanted words, or for privacy reasons it can delete some words and then give it back to the LLM to give us a new sentence, for instance. So this is something that we can do to basically improve the synthetic data generation by integrating a vision language model in a feedback loop. Something else that we can do is to make synthetic data generation dynamic, because here it's a static generated data, synthetic data generation. You generate data, then you give it to the task model, and then the task model start doing training. But something we can do is to also look at the dynamics of the model training. Like the model that we care about, we can look at the way it converges, for instance, and then we can maybe generate images that are that can maybe accelerate conversions, or improve the model on some tasks. For instance, if after some few iterations we see that our task model is still not able to do a given task, when we evaluate it after, I don't know, 100 steps, we can maybe give this signal to the VLM that will now prompt the generative model to generate the images on a given task. So this is something that also is important, I think, to make synthetic data synthetic data generation dynamic along the training of the task model. Another thing as well that I believe is important is that, like we saw in the beginning, we were talking about closed set semantic segmentation, meaning that you have images, you have a fixed deep learning network that is trained on a fixed set of classes that can only segment a fixed set of only a fixed set of classes. This is how it started in the beginning. With Clip, we saw that we are in a, now we have open vocabulary semantic segmentation models, which basically you have text prompts, you have images, and then you can segment any image you want. But basically, in all these methods that we have today, we assume knowing which classes we want to segment, because in the text prompts, you put the classes that you see basically on the image, right? Like if you take an urban scene road, an image with cars and pedestrians, but in the text prompt, you put lion, zebra, and elephant, the clip model will segment all the pixels as lion, zebra, and elephant, even though it's pedestrians and cars and sky and vegetation. And this is a problem, actually, because in open vocabulary semantic segmentation, we have an assumption. We make an assumption is that we know the classes that we want to segment. Yes, we put them in text prompts, but we already know what we want to segment. In some cases, you don't know what you want to segment, and in this case, it becomes what we call vocabulary-free semantic segmentation. And basically, it involves having a, for instance, a VLM again, where you give it input images. The VLM recognizes all the classes that are in the image, and then you use these text prompts that are given by the VLM to the clip model to segment the images. And this is called vocabulary-free semantic segmentation. And in this case, you erase the human in the loop, and you only keep it like fully automated. You are given an image, you don't know what you see in the image, but still you can recover all the objects in the image. So this is slightly different than open vocabulary. It's called vocabulary free, but it also induces many challenges, such as like recognizing all these small objects in the image. And yeah, it becomes more difficult when it comes to high resolution images and then like small objects in the middle or something like that. VLMs today struggle also when it comes to spatial recognition, especially if you have like really high resolution images. And yeah, as broader perspectives, I would like to talk about three things. The first one is that domain adaptation. This is something that I get asked a lot, like whether domain adaptation is still relevant in today's era where we have foundation models that have like a huge pre-trained knowledge that can work really well on, they have like really good zero-shot performance. I still believe that domain adaptation can be interesting when it comes to data poor domains, like macroscopy, historical documents. Sometimes we have like one copy of a historical document that some people found we can have like, for instance, like one historical document that we would like to, for instance, classify or do optical character OCR on these historical documents, and sometimes it can be only one image. And in this case, you still need to do domain adaptation. You still need to adapt to this new domain. So I still believe that domain adaptation has still a role to play when it comes to data poor domains. Something we see today is that we don't want to have a static models. Basically, we are moving from unsupervised domain adaptation to test time and continual adaptation, because we want to have a model that keeps on improving during inference. Today, at least the classical models we used to see in the last years are models that are good, but once they are deployed at inference time, they do not keep on improving. So working on test time adaptation and continual learning is something extremely important in order to adapt to the new incoming domains. And the last thing is multimodal domain adaptation. Foundation models today are really big. They perform really well. They are becoming multimodal, like image, text, audio, etc. And I believe that multimodal domain adaptation, which basically can involve like adaptation on one domain without breaking the alignment with all the others, is something also important. So yeah, multimodal domain adaptation is something I believe that is going to be important because foundation models are integration many modalities. So yeah. So basically, that's it. That's it from me. I would like to thank also my supervisors and my collaborators who, basically helped me during my PhD. I learned a lot from them. So yeah, thanks to them as well.
Cool. Excellent presentation. Yeah. So we may dive into the question answering part of it. If you folks have any queries, please feel free to unmute yourself and ask. If not,
Hi.
yeah.
Hi, Yasser.
Hi.
Thanks for the great talk. It was very insightful. I want to touch on it. You kind of touched on it on your last slide. So this domain adaptation for data poor, like think about medical images, microscopy, or even worse, industrial images where, let's say, a lot of data is IP sensitive, so it's never public, right? So these
Exactly.
foundational models trained on billions, Dino V2 150 million images, Dino V3 billions of images, but they never get to see this data.
Yeah.
And then what we can see is like augmenting data set with diffusion models. Diffusion models are failing to, let's say, generate these images.
Yeah.
So do you have, what's your, I mean, you're quite the expert on this whole domain now. You have these things. What's your insight on this?
I mean, yeah, I agree with you that, of course, like when you have some, like you said, either for privacy or because there is only one document. I saw a presentation like in ICCV, yeah, it was a keynote speech in ICCV where the a researcher was presenting a work about like some archaeologists find out one document. They found one document and they wanted to do OCR on it. They wanted to detect all the characters. And in this case, it's a pure one-shot domain adaptation setting because you only have one image, one object, and you want to do OCR on it. In this case, you are automatically data poor because you have never seen a document like this one. Matter of fact, you actually dig it. You found it maybe 100 meters below the surface. So they found one document. They wanted to do OCR on this really document in a non-invasive way because they don't want to touch the historical document. So they still want to do OCR on it. So this is a classical domain adaptation setting, I think, and it's a one-shot domain adaptation setting. And yeah, foundation models never saw this document, so they cannot work really well on it. They may not do OCR on it in a really nice way, so they will struggle when it comes to this one historical document. And in this case, I think, yeah, using synthetic data in order to generate new historical documents, synthetic historical documents, and then training the model on this synthetic data is probably one of the, I'm not going to say the only way to go, but it's something that will help for sure, because we know that, because we use a classical assumption. The assumption is that when it comes to neural networks, the more data you have, the better it is. So generating synthetic data that looks like this single historical document that some archaeologists found like 50 meters below 50 meters below is the one way to go. Is probably one of the primary things to try. So yeah, I think, yeah, synthetic data has still a lot of things to do, especially when it's coupled with domain adaptation.
Right. Just what I was thinking was maybe techniques like dream booth. Let's say you think about style transfer, but more sophisticated, like personalization of the diffusion models to this target one single OCR image. And then I think we are kind of constrained that if the model works there, so if we are able to, let's say, fine tune the diffusion model to generate the synthetic data of this one single historical OCR image, then I think we are good. But so this is to be, I don't know, but I'm just wondering if, since these models haven't seen this data, they've been mostly trained on natural images. If the diffusion model fails this, so maybe we struggle to do anything downstream. Well, it's just a thought.
Yeah, I mean, definitely, yeah. If the diffusion model struggles to generate synthetic historical documents, then of course it's going to be a little bit difficult. Yes. But then, yeah, it may need a little bit more. Maybe we should look at, for instance, take the diffusion model, look at all the historical documents that we have so far, and then first fine tune the diffusion model using all the historical documents that we have so far, and then we first going to have a first version, which is going to be a diffusion model that is fine-tuned on maybe hundreds, thousands of historical documents, and then from that point on, using Dream Boot to fine-tune to this only specific historical document that we need to do OCR on. So maybe it can be a two-step technique. But
yeah, I think I liked about your talk was this whole pipeline approach of using, let's say, the strengths of different boxes and joining them in a sense. So yeah, you're right. I think yeah, that's would be one way to go and to be
Yeah,
seen.
it's
But
it's
yeah,
yeah,
thank
it's one
you.
way to go, but of course it definitely like we rely on the pre-trained knowledge of the diffusion model. If the diffusion model is not good enough to generate stuff for us, it's gonna be it is gonna be difficult to do
Right.
what we did in this work. Yeah,
Okay. Thank you. Thank you.
no worries, no worries.
Cool. So I wanted to ask about from the world model perspective, specifically the Jan LeCun's approach to that with JEPA. And uh, this was the paper that I was reading today, the Lee World Models. This came out, I think so, today or yesterday itself.
Yeah, it was.
Uh,
Yeah, yeah.
yeah, 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 and they like characterized the latent world model approaches and did uh, 15 million parameter training on a single GPU, and like specifically using JEPA, and this trains like good. They have added a lot of training stabilization features, as well as the data set, the model architecture. And like they discuss in this paper about the planning with both the latent planning, and like how do we uh, go towards the physical understanding. And so do you kind of have any thoughts of like how can you use the your existing research to optimize world models, or like a set of uh, like uh, ideas that could use this your existing research to like uh, pave way for a new like generation of uh, like domain adaptation models that could uh, like in a world model view can automatically uh, generalize to your uh, low resource images that it hasn't seen much.
I mean, I think yeah. I mean, yeah. When it comes to these kind of world models that have a physical understanding,
Mhm.
something that I mean, if we can have a generative model, for instance, or if we can generate data that has that follows physical laws, for instance, because it has been trained on some data on yeah, if we can generate like synthetic data that follows physical laws, I think we may even need like less images to do synthetic data training,
Mhm.
because we would have a better quality of synthetic data. I honestly didn't read the paper, still didn't read the paper yet of the world model, but yeah, I do believe that yeah, if we because it's yeah, synthetic data training is deeply tied to the quality of training data. We know
Mhm.
that training of few high quality images is way better than training on millions of low quality images.
Mhm.
And yeah, adding physical understanding is something definitely it's something that will definitely help, because at the end of the day you want to have a model that can interact really well with its environment, and the environment is deeply tied to physical laws. So generating data that already depicts some physical laws is definitely going to be helpful.
Yeah, true.
That's
And like
that,
with
that for me,
the
that's not possible. Yeah.
yeah, with the recursive approaches too, like I feel like specifically maybe you have heard about the ARC AGI challenges, and the team that led the ARC AGI to use the small recursive model, 7 or 8 billion one, to uh, uh, that was specifically for going into the challenge of unknown problem set. And what they used was they also generated this synthetic data, which had multiple like uh, generalizable features that they could have they could use in their training pipelines, which actually helped them to uh, like win the ARC AJ2 on Kaggle. That happened last year. So maybe combining that with the recursive and and plus your low resource, or like your uh, uh, images that, or your data that isn't uh, uh, spread, that can be used here too.
Yeah, definitely, definitely. Yeah, I agree. Thank you.
Uh, Anything else?
I have a question.
Yeah.
Thank you
Yeah,
for the talk, firstly. I have the question, like it's a more technical question from the third paper, the FLOSS paper.
yeah, yeah.
So I like the way like you deal with the template selection based on entropy. That's
Mm-hmm.
like a good metric, in my opinion. So what I was thinking is, did you guys ever thought about like doing this selection of template like in an end-to-end fashion, for example? I was thinking maybe you can learn a vector of weights, or like a weighted vector selection, and then you
Definitely.
let the model based on entropy loss or feedback signal, and then you let it do this instead of like you a person. Like obviously, it will be tedious for like
Yeah,
for a few tasks, for a few
yeah,
it's
yeah.
okay.
I
But like,
mean, that's a nice question. Yes, I mean, we can do that. Like maybe if you are referring to prompt learning, basically it would be a kind of prompt learning thing, because we would let the model by doing gradient descent, like selecting or giving weights to all the templates, and the weights will be something between 0 and 1, and also summing up to 1 after a softmax, for instance. That's, yeah, this is something that we can do, but in this case, it would break the training free idea, because in our case, we don't do any training. Like this work, like the template selection has been done without doing any training, of course. The merging was done also without doing any back propagation. So we would break this training-free idea. But definitely, if we want to relax the training-free constraint, yeah, definitely this is something to do. Yeah, prompt learning, to do prompt learning, and then of course, yeah, letting the model even like find other prompts, because here we are selecting from 80 prompts. As you can see here, it's 80 prompts. We are selecting from them the best prompts for each class. The best templates for each class. And yeah, as you can see here, it's the grid, it's only 80. But if you do prompt learning and then you let the model choose, maybe you can even find other templates or other regions in the text representations that better segment the class with. But in this case, you break the training-free constraint. In our case, we wanted to keep our model like really light, so we didn't have any training induced in our methods. But yeah, that's definitely something that we can do. Yeah, there's some to let the model choose by doing some gradient descent, by using even some entropy minimization, something like that, in order to go in the direction, what we can call it like direction of expertise for each class, for instance. I don't know if
th-
this answers your question.
thank you for the answer.
Yeah, that is an excellent point too, with the entropy minimization.
For instance, yeah, that's one way to do.
Yeah.
Yeah, just I would like to add something about it. Like entropy was like the first technique that we used, and then we had some good results with it. But after that, we even explored other more complicated metrics, unsupervised metrics. We went into into a research area which is about like unsupervised accuracy estimation, and we
Mhm.
were using other metrics, and we showed some of them in the paper, and we saw that entropy was working really well. Like entropy is simple, but it works really even better than more complicated metrics that were trying to assess the accuracy of the model. So entropy was our best unsupervised metric we found. But yeah, we saw that it's better than 3 or 4 other metrics. But I think that someone can even try to take our work, improve on it, because entropy may not be the best. And for that, even on the GitHub repo, we have a collab notebook that people can use, and then can try to find better metrics than entropy in order to improve on top of our results.
Yeah, true. Specifically, like with this, also you might have noticed about a hierarchical latent entropy mechanism that like uh, has been uh, like shown in the literature that has came out in the past couple of years, in which they're trying out the different layers of latent by a hierarchy, and via this entropy maximization they are kind of uh, templating it and to follow a particular path, specifically in your embodied, like your robotic manipulations and such too. So like that is a very good path to follow too. But
Definitely.
anyways, yeah. I'm digressing here. Any more queries? If not, I think so we can call it a call. Yep. Thank you for your excellent presentation.
Thank you very much, guys. And yeah, thank you for inviting me. Thank you also to all the persons here listening to the presentation. Thank you very much.
Yep.